session. In this session, we are very glad to invite Mr. Hu Changshuo to give us the presentation. And Mr. Hu is a senior engineer who has been working in HRC for around 20 years, mainly engaging in the development and the utilization of small hydropower and other renewable energies, and the research on the application of electrical automation technology. He has successfully presided over or took part in more than 20 scientific research projects in the field of SHP at the national or provincial level. He has designed software of the SCADA system for more than 50 small hydropower stations, both at home and abroad. And as project leader or leading expert, he has taken part in many overseas SHP projects in countries such as Turkey, Pakistan, Macedonia, etc. And today he will talk about the application of SCADA system for small hydropower stations. So let's welcome Mr. Hu.
听到吗？我这个 PPT 就直接开。Okay. Hello, everyone. My name is Hu Changshuo, and I'm senior engineer of HRC. And today we are talking about the application of SCADA system for small hydropower stations. So we have 6 main parts. So first part will be overview the SCADA system for small hydropower plant. The second part will talk about the equipment and the control of the SCADA system. In the third part, we'll talk about the main elements of the SCADA system, including 2 main parts. First one is local control unit, and the second one is computer system. In the fourth part, we'll talk about the communication technology of small hydropower stations, including the communication model, protocol, interface, type, and structure. In the fifth part, we'll talk about the video surveillance system. And in the last part, we'll talk about the centralized control of SHP. First, SCADA system is short for the supervisory control and data acquisition system. Usually refers to a centralized control system which monitors and controls the entire site. It is widely used in industrial processes, including those of manufacturing, production, power generation, fabrication, and refining, and so on. You can see the picture on the right. There is this central control room. It's the central control room of the 3 gorgeous power station. And you can see the many computers and the SCADA system here. Okay, for the SCADA system, we need in the power stations, the equipment under control will from the 4 bay to the tailwater. In the 4 bay, we can measure the inlet gate. We can control the inlet gate. We can measure the water level of the 4 bay. Okay, and in the powerhouse, we can control the generator. We can control the turbine and so on. And in the power lines, circuit breaker, we control this. And in the tailwater, we can measure the water level and control the gauge. Okay, the purpose of the SCADA system in SHP, first is cost saving. Second is increase the productivity, and with better working conditions for the operators. And the design procedures of the SCADA system should be first is safe and reliable. Second one is advanced technology, and third one is meet the requirement from the grid, because we need to send the power to the grid. And the last one is economic operation. So the main functions of the SCADA system in SHP usually including the separatory, means we should see all the data of the site. We should see their status of each unit. We should see the status of circuit break and all the equipment in the power station. And the second is centralized control. Centralized control means in the central control room, from the computer, we can control all these equipment. Okay. The third is auto start and stop. Auto start and stop means with one button, we can start the unit and stop the unit if we need. Okay. The fourth part is the logic control to prevent an accident. So when we do something, when for the SCADA system, when, for example, when we start the unit, we need the cooling water, then we can start the unit. If there is no cooling water, we should not start the unit, because if there's no water in the there's no cooling water in the system, then we start the unit, there will be a damage to the unit. So that is logic control. We need the signals of the cooling water, then we can start. Okay. And the next function is the active reactive power should be able to adjust it according to the setting value, that is AGC, automatic generation control. So we can set the active power and reactive power, and the system should control the unit to the setting value. Okay. The next one is all the data should be recorded automatically, and for fault and accident alarm, and the alarm should remind the operators. Event record and record reading. Okay, all these main functions. That's not main functions of the SCADA system. Okay, then we should see some photos of the SCADA system. The first one is the picture from Turkey, I think. The Turkey project with 3 units, actually 6 units. First one is 3 units with 4.5 megawatts, and the next one is 3.5 megawatts. We can see the computer system here and the LCU local control unit, all these panels, control panels. The next one is also from Turkey. Okay, you can see the next to the unit, you can see the LCU, and in the central control room, you can see LCU2, and we can see the computer system. Okay, with pictures from the site. Okay. In China, the development of SCADA system in the 3 stages of the SCADA system in China. First one is old automatic control system with relays. That is before 1980s. The next stage is integrated circuit control system with transistors. That is during 1980s. And for the third stage, is the computer-based control system. That is after 1990s. And right now, we are doing the next stage, the centralized control system. We'll talk about this in the last part. You can see these are the old school control system, here, with many relays, many meters, many transducers, okay, transistors, okay, with many buttons, switches here. Okay, all these are most of them are manual. Okay, and this is the modern control system. You can see the LCUs and the computer system here. Okay, for the centralized control system, that is the picture we can see here. Maybe we have the several hydropower plants. Maybe it's from 40 kilometers away from the central control room, and we connect all these power stations with optic fiber, with the internet, with many other ways to connect all the information to the central control room, and then we can control all these power stations from in the central control room. So we don't need the people stay in the power station. We can control them automatically. That is what we are doing. The next stage of control system. Okay, this is the structure of modern control system. We connected all the automation equipment, transducers, and sensors through the LCU. Okay, and the LCU will communicate with computer system, and the computer system sometimes will send data to the dispatch center, and sometimes the computer system will directly communicate with the automation, some of the automation equipment. Okay, that's the structure of modern control system. Okay, here also there's many LCU local control unit here. We have local control unit for each unit and local control unit for the common. And we connect them to a switch, and the computer system will connect to the switch and communicate with all these LCUs. Okay, the second part is the equipment under control of the SCADA system, including the turbine. We control turbine by the governor. Okay, yes, governor, and the generator. We control generator by the excitation system, and brake, circuit breaker, valve, pump, air compressor, and so on. First is governor here. You can see here on the left part of this picture. So that picture, you can see the governor here. Okay, the governor controls the guideways of the turbine. Okay, and to control the flows go through the unit. There is a small governor here. You can see for the horizontal part of the unit. Okay, this is the excitation system. The excitation system will control the current. Excitation current goes through the rotor, right? And to control the magnetic field of the unit. And on the right part of this picture, we can see the temperature measuring and brake system here. This LCU, and the temperature is very important for the unit. And if the temperature is very high, the cost will cause damage to some of the moving parts, especially for the bearing and bearing pad. We use bearing pad to hold the bearing, and when the unit is running, the bearing pad, the temperature of the bearing pad will rise. If the temperature is very high, it causes the damages. Okay, so we put sensors in the bearing pad to measure the temperature of the bearing pad. Okay, and then we connect the sensor to a meter. And in the meter, we can see the temperature of the bearing pad. Then we set the high limit of the alarm temperature and the trip temperature in the meter. If the real temperature reaches the alarm temperature, we can see an alarm signal in the SCADA system. And if the temperature goes higher and reaches the trip temperature setting value, and we can see a trip signal from the SCADA system to stop the unit immediately. Okay, in the power station, we can see many circuit breakers. The circuit breakers will be used to control if the unit or the power station to connect or disconnect to the grid, and we can see these signals from the SCADA system. Okay. Man valves in the power station, we can see many valves, including the man valve, including valves for the cooling water, and so on. So valves is very common. We can see a lot in the power stations, and we need to control them automatically. Okay. Pumps usually for the we can use pumps for the cooling water system here. Okay. here we need putting water in to go through the unit to check out the heat from the unit, and the cool water here and go through the unit, and the temperature will rise and take the heat. So we use pump to give the pressures for the cooling water sometimes. And another application for the pump is the drainage system. Okay, in the power station, normally we have a drainage wire to connect the waste water of the power station. If the water level of the drainage wire goes high, we can use pump to take out the water. Okay. Air compressor. Air compressor will be used for the rack system to stop unit. When we stop the unit, when the unit speed reaches normally under 35% of the ready speed, we need to stop unit immediately. So we need to use a brake system, and we are use air compressor to give the pressure for the brake system. And the water filter. Sometimes we use the water filter will be used for the cooling water system. Sometimes the water is not very clean, but the cooling water pipes is very small. So we need to use the water filter to make sure the water is clean, in case to prevent some small sands, some small rocks to block the cooling water pipes. Okay, in the third part, we will talk about the main SCADA elements. Normally, the SCADA system in the hydropower station consists of local control unit, as we have talked about, and the computer system. Okay, the operational priority of LCU should be higher than the computer system. Okay, normally we can stop some operators doing some operations from the computer system in the next to the LCU next to the local control unit. Okay, the first we'll talk about the local control unit. LCU normally consists of a programmable logic controller, that is PLC, and the electric parameter meter, EPM, okay, touch screen, synchronization device, protection device, power supply, air breaker, relay, indicator lights, and buttons. You can see the picture of the LCU here. The main functions of LCU are the first is the automatic unit stop control. Okay, we can control the unit automatically from the LCU. And the second is automatic active and reactive power adjustment. The third is fault signal alarm. When there is a fault for the system, we should see from the LCU and remind the operators. Okay. And emergency stop. Some damage problem happens, we should stop the unit immediately. Okay, that is, we have another sequence to stop the unit, and communication with the computer system, and also unit control according to the computer system. We should communicate with the computer and receive the commands from the computer and operate according to the command. Okay, the most important part of the LCU is PLC. A PLC is an automatic device which can replace the normal relay control system. Simple to install, easy to use. Okay, compared with the modern system and the older computer system, SCADA system, the most change of the system is that we use PLC. Okay, we use the PLC replace all these transistors and relays. Okay. The PLC was invented by Dick Morley in 1969. The first PLC was called Modular Digital Controller, so also known as Modicon. So Modicon Modicon brand is a brand of PLC now owned by Schneider. It's a type of Schneider PLC in Modicon. This is the some parts of the PLC. First, all the PLCs have the same basic components. These components work together to bring information in the field from to the PLC from the field. Okay, we have the input motor of the PLC. That's the input motor of PLC, and evaluates that information and send information back to the field. Evaluate, we use processor to evaluate the information and send information back to the field by output motor. Okay, without any of these major components, PLC will fail to function properly. The basic components, including power supplier, central processor, input and output motor, communication motors, and so on. Okay, that's some basic components of PLC. Okay, here you can see this picture. We connect all the sensors, sensors to the PLC, and the PLC will also connect to some equipment to be controlled. Okay, PLC will also communicate with the computer and connect to the touch screen. That's the logic feature of the PLC. This distinguished feature of PLC is as follows. First, it is good flexibility. The control sequence can be changed easily. Okay. The high reliability is suitable for industrial use. The mean time between failure of PLC is more than 5 years. Okay. We feel the PLC is very reliable. Okay. And perfect function. The PLC has many functions, including digit and analog input-output, logic and operation timing, and all these functions, and easy to use and maintain. If some of the part of the PLC is broken, we can just change this part of the PLC. Okay, in the control system field, we separate signals to digit signal and analog signals. For the digit signals, that is, they are open and closed. It shows the status, working status of some equipment, including open, close, start, stop. It has only two status. It's 0 or 1. Okay, yes or no. That's digit signals. And also we have analog signals. Analog signals includes the voltage, current, power, energy, temperature, water level, pressure, and speed. So we have some motors for the PLC. This is the analog input motor, okay, to provide the required interface for the connection field devices that generate analog signals to the PLC. Okay, the motor this motor employs an analog to digit converter to convert the incoming signals to the binary value. And this is a digit input motor. Here you can see if the circuit between any terminal and the public terminal is connected, the status of this terminal is on, otherwise it's off. So for the PLC, we have many input and output digital motors and analog motors to get information and send information to the field. Okay. Okay. Then we can see some sensors, field devices to connect to the motor. The first one is the position sensor. We can use the position sensor to connect to get the status of the maybe the gate position. Okay, we can put the sensor maybe when we open the gate of the power station. For example, open the gate of the 4-bay, and we put the sensor when the gate reaches this position sensor, we can see fully open stator. And when we close the sensor, when we close the gate and the gate reaches this sensor, we can get a position signal of the gate is fully closed. Okay, the next one is flow sensor. We put the sensor into the in a pipe. If there's flow in the pipe, we can see the indicator of this signal. You can see a signal. If there's flow in the pipe, we use this sensor to check if there is cooling water in the power station, in the generator. Okay, the next one is pressure sensor. We can see if we want to see the pressure of the oil system, we can see the pressure of the air. We use this pressure sensor. And the next one is water level sensor. Water level sensor will be used to measure the water level of a 4-bay, the tailwater, to measure the tailwater and to measure the water level of the water collecting well. Okay. Temperature sensor also very widely used in power station. It's very important. We have talked about the temperature is very important. If the temperature is very high, that will cause damage for the system, for the cell system. So we put the sensors in the area we want to measure, and we get the temperature of this part. Okay. And the next one is opening sensor. Opening sensor will be used to measure the opening of the guideway. Okay, or the opening of the gate. Okay. The next one is the touch screen. Touch screen is an interface which allows the user to get to PLC. Users can see the data in PLC and send commands to PLC by the touch screen. Okay. You know for the PLC, it's difficult for the user to see all these data in PLC. So we need the touch screen to provide an interface for the users to see all this data if you want to see. Then we will talk about some of the interface of the touch screen. The first one, this is the interface for one project, right? From the Turkey, I think, and we can see many digital signals from here, like inlet gate open, inlet gate fully closed, upright bearing flow switch, air cooler flow switch, and so on. These are the digital signals from the power station for this unit. Okay. And on the right part, you can see some analog signals here, like guideway opening, excitation voltage, unit speed, and so on. So, and on the bottom, we can see some buttons here. We can control some of the equipment of the unit here by click these buttons. Okay, first, we can see this is the interface for us to control the main valve. Okay. First, we need to all this before we do some operation. We need to check the conditions for turning off or turn on and turn off this valve. Open or close this valve. So to open this valve, we need the guideway is fully closed. The signal and the signal of butterfly valve in remote motor. Okay, if we don't have all this signal, we cannot turn on and turn off the valve. Okay, this is the interface for to control the cooling water valve. Okay, for example, when we turn off this valve, we need there's no speed of the unit. The unit is stopped, and circuit breaker power is okay, and no fully closed for bypass valve. Okay. It's not fully closed for bypass valve. Then we can close this valve, cooling water valve. Okay, this is the interface for the start conditions. Okay, when we start unit, we need to meet all this information to have all these signals. Then we can start. If one of these is missing, we need to check all these signals from the start system, and then we can check. If we solve the problem, and then we can start the unit. First is circuit break open plate condition, and the brake is not on. Okay. The third is diode rank is fully closed, and there's no speed, and all this information will be needed. Then we can start the unit. Okay, this one is the interface for the analog gate array. We can see all these analog signals of this unit, like the current, voltage, power, frequency, and so on. You can see these analog signals from the high voltage side. Here we have the fourth signal here. Actually, for the SCADA system, we separated the digital signals to 3 parts. First kind is the normal signals. It just presents the status on-off status of this some equipment. Okay, and the second part, second kind of digital signal is false signals. False signals usually refers to high temperature of bearing, abnormal oil level of the bearing oil tank, cooling water break, lubrication oil break, sharping broken, abnormal oil level of the oil collection tank. Okay, all this with one of these signals, the false signals means there's some fault of this equipment, but it can continue put in operation. It just reminds the operators to check all these problems. The third kind of the digital signal is the accident signal. The accident signals usually refers to electric power protection signal, over speed, sharping broken, and emergency stop, over temperature of bearing, lubrication oil break, low pressure of the governor. With one of these accident signals, it means it's very dangerous for the unit. We should stop the unit immediately. So in the SCADA system, if we see one of these accident signals, the unit will be stopped immediately. And if we have one of these systems, and the unit cannot, if the unit is stopped, we cannot start it again. Okay, if we start, then will cause further damage to this unit. So that's the accident signal. We can see some of these accident signals from the touch screen here, and false signals, and protection false signals here. And these are the normal digital input monitoring. And also we have the information query, because from the touch screen, we can, when an accident happens or a fault occurs, or normal digital changes, we can see the time, changes the time and the description here. And this is the interface for the unit stop sequence. Okay, when we start the unit, it shows the sequence, how the SCADA system control the whole system, how to control the breakers, how to control the excitation one by one, and start and stop to stop the unit. First, we need the start ready lamp. if we have this signal means we meet all the information for the unit to start. Okay, the unit is ready to start, and then we will stop the heater. If we have the heater for the unit in some cool area, or not cool, I think it's cold area, we need the heater to keep the temperature of the unit. Sometimes we use heater. Okay, and then we will start the cooling water valve. Open the cooling water valve, and if we can see the cooling water indication from this system, then we can start the governor. The governor will open the guide vane, and the unit will start to run. And when the unit speed reaches 95% of rated speed, we will start the excitation. Okay, we will close the excitation switch, and then we can see the voltage from the generator, and then we will start the synchronization device, and then we will close the circuit breaker. Then the unit will connect to the grid and start the operation. And the next one is the sequence for the unit to stop. First, we will reduce the load. When the load is not very high, and we can trip the circuit breaker, and then we will close the excitation. Let's stop the excitation and close the guide vane by the governor. And when the speed of the unit reaches 35% of rated speed, we will use breaker to stop the unit. And then we will reset the breaker, and then we will close the cooling water and start the heater. That's a sequence to start unit and to stop the unit. But sometimes we have the failure stop sequence and accident stop sequence. If we have this, we will not follow that sequence. There's difference. If we go through the failure system stop sequence, we will not wait there to reduce the power and something like that. We will the unit circuit breaker should be tripped immediately, and field circuit breaker should be opened immediately. That's the failure stop sequence. For example, if we have the over temperature signal or low pressure of governor signal or the electric fault signal, we will go to the failure stop sequence. And also we have accident stop sequence here. That if we detect a fire in our station, or we have the shelving broken during accident stop, emergency stop button was pressed, or overspeed, we'll go to the emergency stop. Emergency stop sequence is very similar to the failure stop sequence, and not only, but also we need in this emergency stop we will close the inlet gate. Well, the inlet gate should be closed. Normally, in the normal stop sequence or the failure stop sequence, the inlet gate we do not need to close the inlet gate. But in the emergency stop, we should close the inlet gate of this generator, this unit. This is the interface for the touch screen to control the unit control interface. Okay, here we can see the setting value of the active power and the reactive power here. For the active power is 3,400. Okay, that is the active power setting, and the reactive power setting is 2,100 for this unit. And also you can see the real value of this unit. Okay. Then maybe there should be some differences between the setting value and the real value. It's very close, but there's differences. We call it, there's a dead band of this in the operation. if the differences between the setting value and real value is smaller than that band, we believe that the value is reaches to the setting value. So we will not do some further operations. Okay. On the right part of this interface, we can see we can control the unit to resting, load, no load, online, stop, this status. Okay. Resting means 95% of ready speed. No load means resting and with excitation, with voltage from the unit. Online means connect to the grid. Stop means to stop the unit. Okay. Also, we can set the unit active power and reactive power setting value here. We can see the circuit breaker status here, okay, in this interface. That's about the interface, and then we talk about another very important equipment we call electrical parameter. Okay, the EPM. EPM connects with the voltage and current transducers. It shows the electric parameters of the unit, such as voltage, current, frequency, power, and energy. Okay. And another important device is the synchronization device. This device will regulate the voltage and frequency of the unit automatically from the unit side. When the conditions of the voltage, frequency, phase between the unit and grid are met, means the differences is very small. Okay, then the synchronizer will send a signal to close the circuit breaker to connect the unit to the grid. So this device is also very important. Without this device, we cannot connect the unit to the grid. Okay. And this is the protection device. The protection device monitors the electric system and sends the accident signal to the PLC when a fault occurs. Also very important. And we can see we will use the time synchronization device in the power SCADA system, and this device will receive the time signals from satellites like a GPS system. In China, we can use Beidou system and send the time signals to automation device in the SCADA system. So with this, so the main functions for this device is when there is an accident happens, we should, for example, an accident happens, there are many circuit breakers will trip from into the overstate. Okay, but we need to know which is the main cause of this accident. So we need to check the sequence of each all this. The sequence of this circuit breakers trip. Okay, first, which one trips first, and second one trips in the next. Okay, so with the time synchronization device, we can see the time sequence, and if we don't have this, we cannot see the sequence. So the time synchronization device is also very important for the SCADA system. Okay, the next one we will talk about the computer system. The computer system normally consists of industrial personnel computer, a display, printer, internet switch, and so on. And for the computer system, normally we have two kinds of program to get these programs for the SCADA system. We can use the high-level programming software, or we can use the configured software to make the software for the SCADA system here. And there's advantage for these two kinds of software. For the normally right now, maybe we will use the configured software because it's easy to use and it's very you can see all the colors. All this is very good for this if we use this software. But also we have some which has some disadvantages for this kind of software because it only provides a few the communication drivers. Okay, only we can use the drivers provided by this software. If you don't have the driver, we cannot communicate with other equipment. So in this case, we will use some high-level programming software. We can program this communication driver by ourselves. Okay. This is interface for the computer system. Here we can see this interface is the main electric parameters of the system of the station. You can see here the circuit breaker status and the brake switches status, and we can see the voltage, current, power, frequency, and all these analog signals for the unit and for the grid here. Compared with the LCUs, we have more information. We connect information from several of the LCUs, so we have more information in their computer system. So we can see all the information of the site from their computer system. Okay. This is the interface for the basic conditions of the unit. You can see here. You can see the water level, the forebay. Okay, you can see the water level of the forebay. The pipe here, the penstock here, and we can see the status of the unit, the active power setting value, reactive power and reactive power setting value, and real value. And we can see the cooling water indications here. We can see the cooling water inlet temperature and outlet temperature. We can see the opening of the guide vane. We can see the oil level, and so you can see also we can see the speed of the unit and the status of the brake here, and many information that we can see from in this interface. We can see the main equipment or working conditions of the site here. Unit 1, Unit 2, and Unit 3, the working conditions. Okay, this is the interface for the unit control. Okay, in this, for example, this for Unit 1, you can see if there's alarm here. You can see the temperatures of this unit. This is there. You can also see the status of the switches and circuit breakers here. And also we can see the active power and reactive power setting and the real value here. And also we can control the unit here. And also we can control some equipped devices of this unit, like a seal valve, okay, cooling water valve, and some bypass valve and equipment like this. Okay, so that's the functions of the unit control interface. Also, we can see some real-time alarms here. Okay, we can see the fault alarms, accident alarms, over-limit alarms here. Okay. For example, for the analog signals, we will see we will set a high limit and a low limit. If the real value goes higher than the high limit or lower, and then the low limit will trip alarm. That is the over limit alarm. Will remind the operators to check the status of this device. Okay, and here we can see some date change history records. Here we can search the records by setting the date and search the fault records and accident records. And also we have auxiliary system, including the PLC from the 4-bay and drain system can control the pumps from the SCADA to control the pumps from the drain for the drain system here. And also you can see the rectifier. Rectifier means the power system, UPS system here, alarms and so on. And also we have this information of the air compressor system. We can start or stop the air compressor here. Okay, and also we have the function to calculate the working hours for each unit. For example, if we have 3 units in the power station, and we normally we want to operate this 3 units, the time where in the even, okay, we don't want to always operate unit 1 and stop unit 2 and unit 3. So we will calculate the operating working hours for each unit, and that's this function. Okay. Also, we have the trend history trend and real-time trend system interface here. If we want to see the history of the analog signals, we can add the pane here in the trend, and we can see the history. We can see the trend here. And also we will there's a report. This is interface for the report. In China, for this analog main important analog signals, we will record this, especially for the electric signals like voltage, current, power, and the frequency. These electric signals, we will record them every hour, each hour. Okay, once an hour. Okay, so we will 24 records for the unit, and then we can see a report here. Of course, the safety is very important. We have to the interface for the safety control. When you want to control the system from the computer, you have to log in first. Okay, this is the interface for login and log out. Okay, in the fourth part, we will talk about communication technology, including 5 parts. The first one is communication model. The second one is communication protocol. The third one is interface. The fourth one is data link, and the fifth one is structure. Communication model. There are 2 kinds of communication model widely used. First one is CDT, cyclic data transmission model, and polling model. CDT model. In CDT model, the device keeps sending data in kind of data format. This model is widely used when a power station sends data to the regulators of the grid, to the dispatching center. Okay, there we can see there's a device 1 here, and device B will receive data information from device A. So device A keeps sending data to device B. This is CDT model. The most widely used model is polling model, known as ask and answer model. In this model, there is a master device and a slave device. The master device will be a computer or a PLC, will send date command to the slave device, like ETM, temperature meter, or PLC. And when a slave device receives a correct command from the master device, it will respond. They send response data to the master device. So the device that you can see here, device A and device B. If device A wants the information from device C, device B will send command to device B. If then device B will receive the command and check the command. If the command is correct, will respond to this command and send that back to device A. Okay, that is the morning model. Okay. Normally, a slave device has an ID number, so we can connect several devices together. Okay. The master device should communicate with them one by one. The command from the master device included the ID number of the slave device. Okay, here there is this computer. Okay, well, the computer will communicate with 6 PLCs. So the computer will first send a command with the ID number 1. Okay, and all these PLCs will receive the command, but only the PLC with the ID number 1 will respond to this command. Okay, and in this model, the computer will communicate with PLC 1, then PLC 2, and PLC 3, PLC 4, 5, 6, and then back 1, 2, 3, 4, 5, 6 in this model, one by one. Okay, communicate with them one by one. Okay, the second part is communication protocol. A communication date between the master device and slave device should follow a protocol that both master and slave device can understand. It's like a language, right? So the communication protocol is usually designed by the slave company. So if you want to communicate with PLC, you will find the protocol provided by the device PLC company and read the protocol and communicate. The products from big companies like Schneider, Mitsubishi, Siemens have their own protocols. Okay, and for the most famous and most widely used protocol is Modbus protocol. Okay, Modbus protocol is a protocol from Schneider company, which is the most widely used protocol in small hydropower station SCADA system. But this is the structure of the Modbus protocol. For the commands, we have the device address, means the ID of the slave device. Okay, the function code means I want to read the date, I want to write the date. Okay, that's a function code, and the big bytes here and error check. That's the commands, and also we can see the response message, answer response message from slave device. Okay, the third part we'll talk about some of the interface, communication interface. The widely used communication interface are 3 kinds. First one is serial port communication. We communicate with serial port like IS-232, IS-485, IS-422. That is a serial port communication. And the second one is the serial device server. Okay, we change the serial port to network. Okay, so we can find this device by internet, by the network, and communicate with this also by the serial port. And the third one is Ethernet communication, like Schneider Modicon PLC, and it is more and more popular for the SCADA system. We just connect to this device to the Ethernet port, and then we can find this port and communicate with this device. The first one is the serial port, IS-232 port. The IS-232 standard was defined by Electrical Industrials Association, known as EIA, in 1969. And normally we can receive this port interface on our desktop computer here, and maybe we cannot see. We can hardly see this interface right now. We can see this interface from the old computers. The features for the IS-232 port the first is the point-to-point. The one point normally only communicate with one device. The second feature is the distance between the device and the computer. Maximum distance only 50 meters. Okay, only 50 meters from the port to the device. So it's not very widely used right now because we are using another serial port. This is the IS-485 port. This port was defined by EIA after the definition of IS-232. It is most widely used interface in the SCADA system. Normally, we can see we can use a converter to get IS-485 port for the computer. Okay, we put this, insert this IS-232 part in our computer, and we get the IS-485 port. The features for IS-485 ports, first one is one port can communicate with many devices. Normally, we can connect many devices to one port, and the distance between device and computer, and also the distance between the master device and the slave device can reach to 1,200 meters maximum. So it's very long distance. You can use it's much better than your IS-232 port, serial port. Okay, for the SCADA system, if there's not enough serial ports to communicate with devices for the computer system, we can use the port extension card. We put this card in our computer, and we can get more serial ports here. The second communication interface is the serial port server. Okay, serial port device server makes the choice for connecting IS-232 or IS-485 serial device, such as PLCs, meters, and sensors, to an IP-based Ethernet lane, making it possible for the software to access serial device from anywhere of the local lane or the internet. Okay, we convert the connection from the internet. We can find this. We connect this to the in the switch, and we find this device, and we can communicate with the serial port of this device. Okay, the best communication port, I think, is the Ethernet port. But it's very expensive, maybe 10 years ago, but it's more and more widely used today. And for some kinds of PLCs and many devices, we have see this port, Ethernet port, used for communication. We just connect the Ethernet port to the switch, and we can find this, set the IPs of this port, and find this port. We can communicate with this port. Okay. This is the Modicon PLC from Schneider. You can see the PLC this interface here. Okay, then we will talk about the indication lights of the communication interface. Most communication interface, like communication module or PLC, serial device server, has indication light to show the communication status between two devices. Okay, we can see, maybe you can see for the serial device server, you can see ready, the indication lights for the ready, for the link, for P1 and P2 here, you can see. And for the communication model of the PLC, you can see the indication lights of RD and SD here. The functions for the indication lights will will choose the indication of communication to the operators. But when the failure for the communication, for example, we cannot see the data from this device, so we need to check the problems. So we can see this indication lights. For example, for the PLC, for the communication model here, if we can see the RD indicates lights, indication lights link. So we will know that we can receive commands from the PLC, from their computer, right, from the master device, and cannot. But if we can see the SD is not blinked, indication lights is not blinked. So in this case, we need to check the program. We need to check the commands from the computer. Okay, if we can see SD blink, normally the communication is okay. If we still cannot see the correct values of this device from this device, we will see the program. We need to check the program if maybe some changes, that is a program problem, not the communication problem. If we cannot see all this light blink, we need to check the communication cables. Maybe the cables is not connected correctly. So that is indication lights will help the operators to solve the problem. Okay, then we will talk about some of the communication link, including cable, network, cable, operation, optic fiber network, GPRS modem, net bridge, radio modem. Cable is very widely used. Will be used for the connect the IS-485 or IS-232 communication modem of the equipment directly to the computer communication port. This is the cable communication. And also, we use the network cable to communicate. It's suitable for a simple and short distance network without electrical magnetic interface and lighting. Okay, we have here. We need to pay attention that the distance for the network cable only 100 meters. Okay, maximum. If the distance between the switch and the device internet port is more than 100 meters, we cannot use the internet network cable. Okay, then in that case we need to use the optic fiber here. Okay. Optic fiber are long, thin strands of very pure glasses about a dimension of a human hair. This is the optic fiber. There are two kinds. Okay, there are arranged in bundles called optic cable and used to transmit high light signals over a long distance. There are two kinds of the optic fiber. We use first one is the multimodal optic fiber. The distance for the multimodal optic fiber only about 2 kilometers maximum, and another is the single modal optic fiber can reach the communication distance can reach 220 kilometers maximum. So if we want to communicate with devices for the long distance, the best choice is the optic fiber. Okay. This is in the some of the components of the optic fiber. Okay, we connected the optic fiber to the terminal box here, and we connected the terminal box to the converter with this small cable, and then we can convert this light signals to electric signal to Ethernet port. This is the optic fiber fusion splicing machine. Okay. One kind of the special optic fiber is the optic fiber composed overhead ground wire, OPGW. This is a type cable that is used in the construction of electric power transmission and the distribution lines. The optic fiber is composed in the grounding wire of the power station power transmission line here on top. Okay, it composes the optic fiber in this lightning in the grounding wire here, and we can communicate with the long distance wherever the transmission line goes. We can communicate with devices of this equipment. So this are the features of optic fiber. It's less expensive. It's very cheap, I think, in China, very cheap, and it's very thin and higher carrying capacity. The capacity is very high. Maybe if we want to communicate with a large capacity requirements, and we need to use this, and less signal degradation, low power, lightweight. So it's a feature advantage for the optic fiber. Another communication link is GPRS model. We have two kinds of GPRS model. The first one is serial to internet. So we can find this device from the internet, and this device can convert to a serial port. So we can communicate to this serial port. Okay. Another GPS model is serial port to short message. Okay. This is, we have an application in Macedonia here. Okay. This power station is very small, and it is in a very wide area. So we don't have, it's difficult to us to connect them to use the optic fiber, to use cables. So, but one of the advantage is that we can find the cell phone signals. Okay. So we use this GPS model to control the unit. For example, we sent one to the short message. For example, we send one to this cell phone number, and that means to start unit, send two to this cell phone number, and that means to stop. 3 means to see some real working status of the information of the unit, and if there is an accident or some fault occurs, and also this device will send short message to the cell phone. Okay, that's the GPS model. And the next model link is we can use NetBridge. Okay, for the NetBridge, only this we can see two parts. If there is no block between these two parts, we can connect them by the Ethernet. Okay. In China, the longest distance, the maximum distance for this NetBridge, we can use this for 60 kilometers. If there's no block between these two devices, we can communicate with this. That is the application case for the NetBridge. For example, there is a reservoir here Okay, we want to see some live videos of this along the reservoir, so we can use the net bridge to communicate with the communicate center. Okay. And also we can use radio modem to communicate. Okay. This is the modem radio, use radio. And in China, especially in China, if we want to use the radio modem for the communication, we need to apply the frequency and pay money for the frequency every year. Okay. And also we can use the internet or cloud for the communication. For example, we can convert the information in the power station to the internet to a server, and we can see the data on the internet. So with this data link, we can see the information wherever we can see. Maybe on the train, we can check the information on the site by our cell phone. Okay, with cloud. Okay. In the first part, we'll talk about some communication structures. First one is communication type A. There are many structures of the communication. Type A, this is type A. For type A, we use IS-232 serial port for communication. For the computer, we're connected to some of the LCUs by IS-232 serial port. It's hardly used because the low the disadvantage of IS-232 port. So we will use the in this case we will use IS-5 port for the communication. In this model, we can communicate more devices with the port from the port. Okay, from one port, we can get more information for the computer. Okay, type C, we can see we use the serial device server for each LCU. So and all this serial device server will connect to a switch, and we use Ethernet cable to communicate for the communication. Okay. And this one is use Ethernet for the communication. Okay. You can see for each PLC we have serial port. We communicate with all these devices by the serial port. Okay. For type C, all these the computer will communicate with all these PLCs, with all these EPMs and energy meters here, communicate by computer. But for the type D, the PLC will communicate with governor, with excitation, with the temperature meters, with EPMs, and then PLC will be communicated as a slave device to communicate with the computers. So more information can be collected to the computer. Okay? And for type E, we have a ring, optic fiber ring here. Okay. The advantage of the type E is that we use many switches to form a ring here. If one of the switch is filled, we can still communicate with others. Okay, this is type E, and we have type F here. In type F, we have double rings here, 2 rings here. For type F, even one of the switch is filled or one of the PLC communication ports is filled, we still can communicate with all these devices. Okay. The more complex of the SCADA system, the more cost it will be. For the Tech 1, the price of the PLC, for example, for one set of PLC. If we use type A, the PLC can very cheap, $150 for type A. But for type B and type C, the price for each stage of the PLC will reach 300 or to $900. But for type D and type E, it's very expensive, which is 6,000 to $8,000 for each stage of the PLC. And for type F, it's very expensive. Okay, 25,000 for one stage of PLC. So the type B and type C is most widely used structure in China for SSP, but for type F, it is hardly used in SSP due to high cost. So maybe it can be used for some large hydropower stations, like 3 GHz projects like this. So because of the cost, it's good, but it costs a lot, so we don't use it. So let's take a break. Okay, we will continue in 15 minutes later. Okay. Then we will talk about the video surveillance system. Okay, let's continue. The fifth part, we will talk about video surveillance system. Video surveillance system is also known as closed circuit television. In SSP, CCTV system may be used to observe important parts of the plant from the central control room, especially for the generator, the bin, switch cabinet, transformer, ball bay, water lever, and so on. This is okay. Main equipment of radio surveillance. Normally, the CCTV system includes some cameras, a digital video recorder, and also known as DVR. Or right now we are using NVR, network video recorder, and a monitor. Okay, this is the structure of the CCTV system, and we connect all these cameras to the DVR, and DVR recorded these videos, and we can use a monitor to get into the DVR and see the videos. There are two kinds of cameras may be widely used. First is bullet camera, and the second kind is the dome camera. The bullet camera, it can be used for a fixed area, because it cannot for for a fixed area, and it's cheap. And for the dome camera with PDZ, it can be used for a wide area, and it's very expensive. Normally in China, for one bullet camera, it's about $60, and for the dome camera, it will be $150 to $400 for each dome camera. For the digital video recorder, DVR is an electronic device that records video in a digital format to hard disk, and it provides software to review the video stored in the hard disk. The video recorded in the DVR will replace the old video when the hard disk is full. Okay, so we can calculate the date for each hour. For example, we have 6 cameras. We can how long we can use. How long for the hard disk can store the live videos. Okay, that is the formation for this equation for the calculation. Okay. And for the display, we have one display or a tied display. A tied display connects multiple displays together with cables and the main controller. Okay. This on the right side of this picture shows the tied display, and this is the interface for the DVR. We can select the cameras, and you see the live videos for the cameras, and also we can control the zoom camera from the DVR here on this interface. And for the last part, we'll talk about the centralized control of SSP. This is what we are doing in China. Okay, so first we'll talk about the background. Because of the Chinese rapid economic growth, the wages cost is taken more important part of the cost of SSP operation. So take Zhejiang province, for example, which the power price is one of the highest area in China. We have peak hour and the valley hour. Peak hour is from 8 a.m. to 10 p.m. The price for the electric is about 8 cents dollars, and for the valley hour it is about 3 cents, and for the average price for the electric is about 6 cents. And the problem is this price has not changed for more than 15 years. So monthly, the salary for the operators, for each operators in 2000, it's about $200 a month, but in 2020, the salary will reach about $1,000 every month. Okay, so the salary for the operators increased quite a lot. So take the 500 kilowatt capacity power station, for example. Maybe we have four operators. Four operators. So the energy production it's every year we will maybe in every year the unit can be put into operation for about 3,000 hours normally. So the energy production for this power station is about $90,000. And for the labor cost in the year 2000 will be only about 9,600, taking about 7% of their production. But in the year of 2020, it reaches $48,000. It will take about 55% of the production. So it is getting more difficult for SHP, especially for those with the capacity under 500 kilowatts. So they cannot make money by if their capacity of the power station is smaller than 500 kilowatts. Another problem is that normally SHPs are built in the mountainous area, which are far away from the urban area. Because of the low profit of SHP, and they cannot afford high wages, so people prefer to find their jobs in the city. And it is more and more difficult for hydropower stations to recruit employees, even they increase the salaries for the employees, but it is more and more difficult for the hydropower stations to recruit employees. So, and on the other hand, the hydropower station management needs professionals in many specific areas. We need professional employees in the electric. We need in specialists in the electric. We need a mechanic. Okay, so that is a challenge for the SHP in China. Okay, so another background is compared with 15 or 20 years ago, the monitoring technology has developed greatly in security surveillance, network information display, electronic components, and software, which can support the centralized control system. And so the monitoring technology has changed a lot. So we can see the equipment such as video surveillance, smoke alarm, and access control used to be very expensive. And these devices are not only cheap, but also have more functions right now. Okay, maybe 20 years or 15 years ago, this device can be used in some areas, but it's very expensive. It's not used for the SHP, okay, cost effective. So, but right now we can widely use all these equipments. For the video surveillance system, can not only be displayed in the field, but also can be transferred through internet and displayed far away from the cameras. So first, we use analog signal system for the monitoring system, for the video surveillance system. And the next page, we can use a switch, okay, to connect all these cameras. We use network cameras Okay, and then right now we can use the NVR can connect to the internet, and we can see the live videos far away from the cameras, okay, through the internet. Another development is the communication technology developed very fast in recent years. It was very expensive to make an internet call about 10 years ago, and now we can have a meeting online like this, like what we are doing now. And thanks to the development of video compression technology and the communication technology, we can use enough bandwidth for live video transmission. And for a SHP with 20 cameras, 100 megabits of bandwidth is required. Maybe 10 years ago, we can only transfer 1 or 2 cameras through the internet or through the Wi-Fi, but right now we have more bandwidth. Okay. And another technology development is the display. With the modern display technology, a great amount of information such as live video, real-time date, alarm can be presented to the operators so that they can understand the real situation better. But it's a challenge to display such huge amount of information. So we can use this. You can see the very large displays to display all these informations. And also we have development of some sensors of the SCADA equipment. For example, maybe 10 years ago, if we want to measure the high voltage part of the temperature of some of the high voltage parts, like the transformers, the connectors of some of the cables, we need to use infrared cameras. But the price is very expensive, around $2,000. But right now we can use wireless sensor. Okay, the price is very cheap, about $230 for each stage. So this device can be widely used. And 10 years ago, most communication ports is serial port communication. And right now we are using the internet communication. So we can communicate all these devices for a long distance. And another development is software development to developing tools. Maybe 10 years ago, we used the high-level programming software or configured software for the SCADA system. And that's the disadvantage of this kind of developing software is that this software can be installed on one computer. But right now, we can use a web to developing tools. So we are using a web to access the SCADA system, and we have the software for the apps. So we can see the information from our cell phones. That is the software developing tool. So what we are doing, what we want to do is centralize control of the SHP. With the computer technology, the central control room will communicate with all the cascade hydropower stations. So one group of staff can operate all the power stations. And for the centralized control of SHP, we need to update the SCADA system of SHP. For each SHP, we need a reliable SCADA for each site, and then we will need a control platform for the SCADA system, and we will in the third step is that we need a management company to manage the centralized control all these power stations with professional crew to control all these power stations. So for the platform, so for the professional for the in the central control model, the platform operators will be separated two kinds, two groups. One group will respond for the platform operator. They will do the online surveillance, online inspection, remote control from internet. Okay, another group of the operators will be responsible for the maintenance and inspection group. That is maintenance and inspection group. They will routine on-site inspection, maybe twice a week or every other day, and equipment maintenance. If there's some problems for some of the equipment, they will check and solve the problems. So we can see here before we use the centralized control for the local. The control model is local, and we need about 4 to about 20 people, operators for the operation. It depends on the size of the SHP, big one or small one, and the management level is not even. There's for some of the power stations, the operators is very professional, but for some small hydropower station, very small hydropower stations, it's the management level is very low. And for the spare parts, before the centralized control, they will prepare spare parts for each side. But after we use the centralized control of SHP, the control model is remote. The operators will control all these unit SHPs or stations from the central control room. So for each site, we need a 0 to 2 about guided. So only 2 people will be needed for each power station, and we will have professional team to manage all this for the operation, and they can share with other share the spare parts and test equipment with others. So that is the difference between the before we use or after we use the centralized control of SHP. So for a centralized control system of SHP project, normally can be divided into 3 parts. First, we need to update the SHP, the SCADA system of SHP, to update the SCADA system of SHP. The second step is that centralized control platform. We need a platform for the control system, and the third is the communication channel. Okay, we will talk about this one by one. First is SHP update. The power station operation in centralized control model would be updated to meet the requirements for unattended small hydropower station. The operation status of the SCADA system of each power station are different, and the invest budget for each power project is also different. So the planning for the SCADA update will be different. We should evaluate the functions, reliability, and safety of the existing SCADA for each power station, and design according to the evaluation results and the investment budget for each for the update. So the updates can be simple and can be complicated due to the budget. if you have more money, we can use more devices for the updates. If you don't have much money, we don't need to further updates. So there will be no operation on duty in the power station in on a tandem operation model. So the general operation model should be first the operators will stay in the central control room to check the conditions by live video or real-time dates each power station and control the equipment in each power station. In case of failure, the site data can handle it automatically. There is no need for on-site manual operation. Okay. The second is in case of emergency, the unit should be able to shut down first, and then the platform should notify relevant person to go to site for inspection. So in case of emergency, we need the station can stop the unit first, and then we send people to check on site. So the key points of the SCADA's update first is safety. Safety measures to ensure the safety of the power station. We will use access control, smoke alarm, cameras, and voice intercom system. And the second is let the operators know as much as possible about the site conditions of each power station. So we will use more sensors, we will use more cameras. And the third is make sure the unit can be stopped in case of emergency. That is very important. Yeah. Okay, this is the fire alarm system. Install sensors where the fire may occur and connect them to the control panel. The controller sends alarm signals when a fire signal is detected. So the controller can connect to a bell or flashlight to remind people, and also can connect to PLC to remind operators in central control room. Okay, this is fire alarm system. Maybe normally we will use this fire alarm system just to prevent the fires of the power station, of each power station. And sometimes we can use access control. The controller for access control system, the controller can open the door remotely from control platform. In case of fire, the controller can automatically open the door so that people can get in and put out fire. So there's a linkage of the door of the gate. Okay, access control system. Another important system is voice intercom system. Voice intercom system connects to the network and allows operators to talk to the power station from central control room. If we can see some strangers go close to the power station and no one in the power station, we can use the voice intercom system to talk to the strangers, to ask the strangers to go away, okay? To remind the strangers. And what is the most important is the video surveillance system. Okay, so this is structure for the video surveillance system. We can use many cameras to connect them to the switch and connect to the NVR, and we can see the live videos from site, and also the live videos will be sent to the central control room. And another for the security, another measure we will use the SCADA system software to update is normally we use Windows system operation system, but for the centralized control model, we will use the Linux system, and we believe that the Linux system is better, more safer for the data readers. Okay. So we need to stop the unit in emergency. So how to stop the unit emergency? That is what we need to think about. So first one is cut off the water supply, and also we need to disconnect the unit from the grid. Okay, two main measures when there is an emergency happens in the power station. What we need to do first, we will need to cut off the water supply, and second, we will need to disconnect the unit from the grid. So how to cut the water? We can see the water. We can close the inlet gate or four-way gate first. Okay, here we can close the main valve, and we can close the guideway. Okay, we can close the guideway by close the governor. Okay, we can close the main valve and inlet gate. So we need to make sure we can do that. So if before the before the update, we should see the real situation of the site. If, for example, if the governor is not very good, in a bad condition, and all it cannot be controlled remotely, we need to update the governor. Okay, here from the left side to the right side, we need to update the governor, and also we need to check the main valve. Make sure we can cut off the water supply. So if it's on the left picture, it's electrical valve, but if it is possible, we want to change it to a heavy hammer valve here, because if for the heavy hammer valve, even we lost power for the power station, it can still to close the main valve. The main valve can still be closed because the heavy hammer here. And also we need to check the four-way gate. Okay, here. This is project from Gershan project. The picture from Gershan project. If before we do the update, that is very old controller here. We use the motor here to close, and then we update the controller here so that it can be controlled remotely. Also, we can use the unit. You can use the linkage, unit emergency stop and slow skate linkage, or water level and slow skate linkage. For the slow skate, if an emergency occurred from one unit, and we can open the slow skate, or the water level of the four-way reaches a high level, we can automatically open the sluice gate. Okay, another important part is to disconnect the unit from the grid. Okay, take this power station for example. We can disconnect the circuit breaker for the unit. Also, we can disconnect the circuit breaker for the low voltage side of the main transformer, and also we can disconnect the circuit breaker of the high voltage side of the main transformer. So we can do it we have three circuit breakers for us to disconnect the unit from the grid, make sure the safety of the unit. And another thing we need to think about there is the power supply. Power supply is also very important for the SCADA system when there's no power in the power grid. DC power, dual power station, switch device or this diesel generator can be used automatically switch the standby power supply. Okay, you can use DC power or the diesel generator for the power supply for the power station if we lost the power from the grid. Okay. In the fourth part is about the centralized control platform. Centralized control platform consists of communication server, application server, and network devices, and display equipment, video integrated platform, and operation workstation and other equipment. So this is the communication topology for one project. There are two communication servers responsible for communication to collect the data from all the power stations. The data will be stored in the communication server and shared with application server. Here we have two communication server and two application server here in this picture. And the operators will use browser to communicate to operation computer from or will use browser from operation computer to access the SCADA software in the application server. Okay, this is the video surveillance topology for one project. All the video signals are transferred to video integrated platform from site NVR by internet. So one computer is used to access the video platform to adjust the video signal displayed on the splicing display screen. Live screen. Okay. For this part, we'll talk about the communication channel. The data transmission between the power station and the centralized control center mainly includes video signals and the SCADA signals. Due to the importance of the data and the different bandwidth requirements of the data, we generally transmit the two signals separately. Because the video signals has low security requirement but large bandwidth requirement. It is normally transmitted through internet. On the contrary, the SCADA data has high security and low bandwidth requirements for the network, and it needs to be transmitted through a dedicated line. The network channel of the video surveillance is very simple. One only need to apply for internet access for each power station and centralized control center for internet server provider. So normally a static IP is required for the centralized control center. Here, for the centralized control, we need a static IP because we need the live videos from NVR for each site will send live videos to this static IP. For the safety of SCADA data communication channel, China has very strict regulations on the power station's communication, which is usually managed by the power grid company the power station connects to. In short, there are three rules for the SCADA communication, SCADA data communication network. The network of the power station must be a local area network. It cannot be connected to the internet. Okay. The second is the network between the power station or between power stations or between power station and the central control center must be a private network, and the data should be encrypted. And for the third rule is that if the power station or control center needs to communicate via the internet, the network must be isolated. Okay, these are three rules for from the grid. So for the network reliability, two communication channels can be applied. We can apply two private channels for two different network provider two ISP, two network providers, or we can apply one wire or one wireless channel for the communication. We can use the wireless channel for the redundancy. Okay. And sometimes we can use a ring network structure for the communication. Okay. For example, the cable will connect site 1 to site B and site 3, and then back to the same the control center. Okay. Okay. For the last part, we will share some projects of the centralized control of SSP. Okay. Actually, two projects. First is Gusan project. Gusan Hydropower Station is the secondary power station of Henjing Power Station, with a distance about 6 kilometers. Here in this picture, you can see Henjing project next to the Red Wall. Okay, and the Gusan project about 6 kilometers away from Henjing project. The two hydropower stations are all managed by Henjing Reservoir Management Division and installed normal SCADA system. So due to lack of operators, the Reservoir Management Division decided to update the SCADA system for the remote control in 2016, so that one group of operators can manage two power stations. So they don't have enough operators for the two power stations. They want to use one group of the operators to operate two power stations. So this project was finished by the end of 2016 and put into operation system, achieved expected results. So let's see what we have done for this project. First is live video monitoring system is added in 4-bay entrance, central control room, a unit interior, especially here, but even in the generator, we put a camera here. Okay. An air compressor room and other important petrol parts of the power station. So the voice intercom system is added to drive away the person who entered into the plant by mistake. Okay, we can see the loudspeaker here. Okay. A water level sensor is installed in the 4-bay to connect to the 4-bay water level here in the 4-bay. And after this, those gates of the 4-bay add the automatic remote control functions and the linkage with the unit accident and 4-bay water level. So if the water level reaches the high limit, we will lift the sluice gate. So this is the access control used for the security. And smoke detected sensor and alarm host for and linked with the SCADA system. So if there is a smoke alarm signals, we will stop the unit immediately and open the door so that firemen can get into to put out fire. And also we use infrared temperature sensor to collect the temperature of high voltage parts. Here, this is the transformer. In this part, we use sensors to collect the temperature of this transformer. And also we use diesel generator for backup site power. And this is the central control room of Gusan project. on the left side is the computers responsible for the Hengqi project, and on the right side, there are two computers responsible for Busan project, and we have the live videos of both sides. And also they have their specification of safety operation for unattended small hydropower station. And this defines the obligation for the management and the operators. And it defines the rules of operation, management, accident handling, temperature inspection of equipment and facility, equipment overhaul, and the maintenance of unattended small power stations. They are using this definition, this management rules. And this is the record table for the how to say, remote video check table. Okay, there are about 31 cameras, and for every 2 hours, the operators will check each cameras, and if they check, they will click if it is normal or it is abnormal for each cameras every 2 hours. And in the last part, we'll talk about the Lambo project. Okay, Lambo company is a state-owned company which manages 3 power stations, including Hepanqiao Power Station, Jiufeng Power Station, Shanghai Second Power Station, with the total capacity of 21,200 kilowatts. They started to change their management model from normal SCADA to centralized control model since 2020. First one of this project, okay, started in 2020. The control room is set in the office building in the urban area and connects 3 power stations with network. And other 8 power stations will connect to this central control room for phase 2 of this project, so that the total capacity will reach about 45,620 kilowatts. They start a team for daily operation, which has about 9 operators. Another team, which has 10 persons, responsible for the routing, patrol, and maintenance. This is the central control room of the Lambo project. You can see the splicing, the large screen here, and the many computers. The operators will sit in the central control room in the urban area to check all the working conditions of the several small hydropower stations. So you can see there are many cameras for this project. The operators should check them one by one, and of course, when there is an accident, the camera screen will pop up to remind the operators. This is the interface for the you can see the station, the working conditions, the conditions of the unit. In this picture, we can see 4 units of Hepanqiao project is in operation. Okay, the others, the units from the other power station is stopped. Okay, you can see this is the structure of the communication. We used some of the security devices to make sure the security of the internet, the network, the safety of the network, and we use the dedicated line for the SCADA system communication, and for the red lines, that is the internet. We use internet for the live video communication. Okay, here this is the interface for the there are about 9 power stations in this project here. And we can see the electrical signal line for each unit here. We can control each unit from the SCADA system, centralized control SCADA system here. First we need to select this hydropower station, and then we can control the units from this power station. And we can see the trend of their signals, analog signals, and also we have their virtual signal line. That is in this interface we can see which unit is live here. It is in the running operation, in the running order. Okay. In the end is the conclusion. The small hydropower industry has entered into a new stage of green and sustainable development, and it faces at the same time the difficulties and challenges of labor shortage, safety, operation, and management. The small hydropower is recognized as a clean and renewable energy. With the new and updated technology, SHP is also always making the significant contribution to the social and economic development. Okay, thank you for your attention. That's my presentation. If you have any question, I will be here for you. You can add my WeChat, okay, or you can write to me, email to me. Okay.
Okay, thanks so much, Mr. Hu, for your informative presentation. So now we will enter into the Q&A session. If you have any question, you can put forward in our chat box.
Mm-hmm. 我这个怎么网络异常断掉了？发现这个应该好了。
So in this presentation, Mr. Hu gave us a detailed introduction of the SCADA system and its application and the small power station. And Mr. Hu also accumulated abundant experience in this field. So if you have any question or you have any comments on today's presentation, please feel free to put forward in the chat box. Mr. Hu will be very happy to answer all your questions. Okay, if you do not have a question right now, maybe we just stop here. And if you have any question after the presentation, or you want to communicate with Mr. Hu, you just come to us, or you can directly contact Mr. Hu. You can find the contact information in our guide menu. So. Thank you, Mr. Hu, for your brilliant presentation. And that's all for our session 1. And our session 2 will be continued at the same time, 6 p.m. Beijing local time. So we will see you there. Please join us on time. See you. Bye.
Bye.